Hello, everyone. Welcome to this presentation on application of Spark NLP for some really exciting work on multimodal predictive modeling on electronic healthcare records. This is collaborative work between four institutions, as you can see, between Pacific Northwest National Laboratory, Stanford University, Virginia Tech, and John Snow Labs as well. So in this particular presentation, I'm going to tell you about a number of things. This is a study that we have been carrying out in the context of COVID-19. So we will show you some really exciting results on a COVID-19 data set spanning over 9 months from Stanford Hospital. And we will show you how, so first I'll walk you through the predictive modeling questions that we're focused on. Then we'll dive into the details of what's in the data. We talk about multimodal models. So where does that multimodal aspect come in? How we create those? How do you create those data sets, and then bake in those multimodal considerations into designing our model? I'll go into the little details of how we use Spark NLP, and then I will finish with details on how we develop our multimodal model for predicting the length of stay for COVID-19 patients, and leave you with some key conclusions. So the beginning, the driver for this work has been that given the background of a patient and given the information we have about a patient during their stay in a hospital, can we predict their severity? So predicting severity of a disease or a patient's condition, it's a well-known problem. And there are many notions about how we can go about measuring severity. We can think about it as predicting if somebody will end up in the ICU, what's the risk of mortality, or if somebody will end up in the ventilator in a severe condition. In this particular work, we have a slightly different approach. So we would like to predict what is the likelihood that a patient would be staying in the hospital after K number of days. We found this need articulated to us from medical practitioners in many institutions, because as COVID-19 has shown that during a course of a pandemic like that, the entire institutional capabilities get severely pressed out of their what they're used to operating under. And being able to predict whether a patient is going to be in the hospital in the next 3 days, 5 days, 7 days is critical for making sure that you have the right supplies. It's critical for securing your supplies and also making sure that you're planning your human resources properly. So that was one of the major reasons we chose to focus on predicting the length of stay as an indicator for predicting severity of a patient. Now that's the goal. Now I'd fall back on the kind of data that we'd like to make use of. So clinicians, as the human experts, they like to look into all the previous history we have about a patient when they come in for the admission. And then, of course, as the patient is staying within the hospital, we are looking at all the lab measurements and then responding how the patient is developing, his or her conditions are developing. And of course, then we see the evolution of the patient being reflected in the drug and the drug codes and the diagnosis codes. So what you'll see here is that how we combine three primary sources of information: the clinical notes that capture the profile of the patient at the admission, the diagnosis codes that capture what the patient came in, as well as the evolution of the patient during the stay, and then the drug codes, or the drugs that are administered to the patient during the course of the stay. And as I said before, this study is done on a 9-month COVID-19 data set collected from 2 hospitals that's part of the Stanford University Medical Center. So there are 2 data sets that we make use of in this work. As I'll elaborate more in the later half of the presentation, that our prediction models is using a self-supervised learning approach. And self-supervised learning approaches, or in general, deep learning models they do better if you have more data. And one of the challenges that we all ran into with trying to bring in these data-driven approaches for COVID-19 is that most of the time we don't have much data for the COVID patients. So we make use of two data sets. One is a data set explicitly for the COVID-19 patients with about 450 patients, spanning from February of 2020 to late of 2020, like October to November, and as well as a multi-year data set that we have from the same institution on consisting about 8,000 patients, nearly 8,000 patients who had acute respiratory distress syndrome. So the intuition or the insight for this, using this two-pronged approach, is that we'd like to train a model, pre-train a model, because our hypothesis is that patients who are having acute respiratory distress syndrome, or ARDS, would be exhibiting a lot of the similar conditions when we go into the COVID context. So can we train a model with lots of data from a bigger cohort with ARDS, and can then we fine-tune it for the uniqueness of, to look at the unique challenges that comes with the COVID-19. The plot on the right shows the distribution also of the length of stay. Again, we plotted the patients into two groups. The blue one shows patients who were, the orange one shows patients we are labeling as severe conditions. These are the patients who were either the patients passed away, or the patients were admitted to a ventilator or into an ICU. So it's quite clear visually when you look at this plot that the patients in the severe conditions had a pretty larger length of stay, and there was a significant variability in the length of stay as well, which again is another driver. The prediction of the length of stay is quite as useful as it is to the caregivers. Predicting length of stay is not also an easy task as well. So how do you go about this? That's what the journey has been for us. So these are the three major data sources. Again, kind of to repeat what I said before, that we make use of the natural language clinical notes. That's capturing specifically during the study. So we try to extract all the risk factors or the prior history of the patient from the natural language clinical notes, in addition to other diagnosis codes or drug codes we can find. Then we also have the clinical knowledge graph that captures the classification. So we have the ontological information that tells us what kind of categories or multiple categories a drug or diagnosis code might belong to. We can also find information what kind of organs a disorder is associated with, and so on and so forth. And then, of course, the top one is showing the diagnosis codes and the drug codes that we have a temporal history during the stay of the patient. So the role of Spark NLP is, so the value for clinical notes is well motivated for years. And it's just that working with natural language documents has always been a hard problem. And so what happens is that even in our past experience, the challenge you often ran into is that you can spend all the time trying to do this extractions with high accuracy, but then you're not left with any time to build a meaningful prediction model that tries to combine the information from the structured data, from the clinical notes, and everything. So we saw the collaboration with John Snow Labs using their Spark NLP toolkit as a big opportunity, because the Spark NLP allows us to go from the clinical notes and extract a structured representation of the data. And that's also kind of been our philosophy, that we would like to take all these different data sources and project them into an unified structured representation, where we have all the diagnosis codes, drug codes, as well as the risk factors, everything we can glean about a patient into one representation. And so what the picture at the bottom, the cartoon shows you, is that in the traditional sense, what you would have normally done is that you have taken in a clinical notes document, and the green circle shows that we just extracted a set of entities and plugged them into an LSTM or some other transformer model. What we are hoping to do with the Spark NLP-like tools is that we are trying to not just work with a set of entities, but we would like to also work with their assertions, the presence or their absence, the confidences, as well as the relationships that might come between a drug and a symptom. That given a patient, did the administration of a drug improve the patient's condition or not? So admission profile factors are really critical, because knowing the history of the patient, so the kind of information you see on the boxes on the left are things that we heard from the doctors. These are the things that they care about. These are the things they like to look when they first see the profile of a patient that's coming in. And as you try to build an AI model, we like to factor in the similar kind of considerations in the design of the model as well. And so what we do is that we effectively take every clinical notes, we parse those into different chunks or chunks keyed by the header, and then we know which headers are we most interested in. And then we can actually go after some of this, the boxes that shows you see on the screen are directly correspond to headers like, say, demographics, past condition, past medical history, social history, and so on and so forth. So what we did next was that we started looking at the temporal history of this entire COVID-19 cohort we had. And then we tried to assign every patient to a time interval, to a month, where the day of the admission, so a patient would be assigned to March if the patient was admitted to the hospital on, say, March 30th. Even if the patient would stay through April, we'd be assigning that patient to March. And this way, we try to sort all the patients by the length of stay, and we try to look at what are the dominant factors associated with them. So we looked at the length of stay. We also looked at the count of all the risk factors that we extracted from the clinical notes. So one pattern, as you can see, one strong pattern that emerges in this picture is that the top 3 risk factors are kind of the same. And then knowing that, I mean, by now we all know that hypertension, prior use of medication, which suggests that the presence of some other underlying problems or diabetes are well-known risk factors. But what this also tells us is that just looking at these top well-known risk factors are not really actionable. But then you look at the other ones, and as you look at the other ones, you can see that they have been changing quite a bit. And the data is high dimensional, so you can look at this. You can look at this data cube and slice it, dice it by looking at race, looking at age, gender, and so on and so forth, and all the combinations. But as you look through the data, we kind of saw this clear separation that we needed to dig in beyond the top 3, and then you can see some interesting insights emerge. And I'm going to walk you through quickly through one of such exercises. So as I said, as you try to slice and dice through these very high dimensional data sets, go looking at the combination of race and age and gender and so forth, we went into another direction as well. We wanted to look into higher order relationships. When I say higher order relationships, this is basically if I have a set of codes, and it can be drug codes or diagnosis codes, but I want to understand what is the collective, which subsets are more dominant, which subsets are more critical in shaping the patient's evolution over time, which subsets observing, which subsets of the admission would be very informative for us to predict the patient's trajectory over time. So in particular, we focused on 2 things. We try to look into the comorbidities, and we also try to look at the set of concomitant drugs, which basically says, here are the drugs that the patient received at a given point of time. And then we try to study the relationship between these comorbidity patterns and the drug, or I'll just call them treatment patterns in short. So what emerged is this picture. So the graph you're seeing on the right is showing the top every node. So if you look at the green nodes in this picture, every green node represents the combination of 3 top class of disorders. So we could given the way we came up with this graph, or this kind of graphs, is that we map every patient into a time interval. So whatever drugs a patient was given within a day, we would bring the patient's data into 12-hour or 24-hour interval. So then we'd be looking at what are the top frequent sets, or using a variation of the item set mining like algorithms, what frequent sets emerge in the collection of symptoms or the condition codes, and what frequent sets emerge in the collection of the drug codes. And then we can build this graph that says that a top comorbidity pattern, which are the green nodes, are related with the top treatment pattern, which are at the pink nodes, if they were administered at the same time. A patient having the comorbidity was given the treatment. And then we could assign age weights into this graph, kind of to understand what is the median length of stay for the patients who had that problem and who received the treatment. And so what this allows us to think about is that a patient with a given comorbidity pattern. So think about looking at a green node in this graph. And all the pink nodes that are associated with the green node basically says people who had that comorbidity had all these different treatments. So if you now look at this graph changing over time, looking at how the age rate changes tells us, is the length of stay improving? Is the length of stay, median length of stay coming down, which would in some way allow us to think about, are we getting better at treating patients with a given comorbidity? So as we did this analysis over time, and we did this by zooming into different comorbidity patterns, some very interesting ideas or insights came out from the data. And this is something that we have submitted to EMEA recently it's a paper under review. But what you're seeing here are each of the plots corresponds to a particular comorbidity pattern. The y-axis for each plot shows the median length of stay, and the x-axis kind of shows the month over month, its time. So if you see this point, the colored dots coming down, it basically says over the period of time, the medical community found a way to treat these patients better. It could be either a better treatment, it could be a change in the population's behavior, whatever it was, but things improved. So if you look into the one in the middle, you can say that definitely things improved for patients who had COVID acute hypoxemia delirium. But for some of the other ones, if you look at the right one, the second one from the right, actually the length of stay didn't flatten or come down. You could say at least it stayed flat, or it might even went up. The same perhaps could be said for the second one from the left, that there was no clear improvement in the length of stay. So this effectively gives us a way to go beyond looking at very coarse-grained indicators just by looking at the risk factors or gender or race, but dive into more of these finer aspects, looking at specific comorbidities, which treatments, first of all, which comorbidities, patients with which comorbidity profiles are getting treated better, where we need to focus, and where the improvements are not happening. And where the improvements may be happening, by looking at the association between the comorbidity and the treatment patterns, it allows us to reason about what might be helping. Is there a shift in the treatment pattern that's really leading to these improvements? The final part of my presentation is talking about the predictive model, where we try to bake in this kind of notion of higher order relationships between drugs and condition codes and other risk factors into the model. So the goal for us here is to be able to build a model that's more interpretable, or in some sense you can say that it's more domain aware. We are trying to bake in all these notions of the clinical insights into designing the model. So our initial starting point has been looking at the transformer layers that's been already explored for electronic healthcare records. In a very quick, in a 30-second introduction for transformers, what we're effectively doing is that we are, as I said, we are binning the patient's information into 6, 12, or 24-hour intervals. So we can build a profile for a patient or a set of diagnosis codes and drug codes for that 24-hour window. And then we can mask, following the BART philosophy that everybody knows now, is we go mask certain entries in that window. And then we use the rest of the data to be able to predict it. And that's that is what we refer to as the pre-training step. And so what we do is that, as I said before, we do the pre-training on the broader ARDS cohort with about 7,000 or close to 8,000 patients. And then we take the same model, but then we try to train it for the COVID-19 cohort, which we refer to as the fine-tuning step. So this slide shows a little bit of the details of the internals of our model. So what's unique about this is that we are of course, we're trying to, the lowest layer shows you how we are integrating different data sources coming from the Spark NLP extraction outputs, as well as the drug codes and the diagnosis codes we have from the structured data. They're fed into the encoding layer, which is referred to as the concept embedding and time encoding. So the interesting thing here is that we're also trying to factor in time. We are also trying to factor in when a patient is getting a blood thinner, what's the offset during the stay? And being able to account for the offset from the beginning of the stay, being able to account for the offset between the intervals last time, what was the last time the patient, or how long the patient has been taking this blood thinner. Those are some of the active ideas that we're exploring in the time encoding layer. And then it goes into the concept relationship learning layer, where we're effectively trying to learn those higher order relations. Which subset of drug codes are intricately related with other set of condition codes. And this is trying to recover the same insight I described with the comorbidity and concomitant drug treatment pattern analysis. So what you see is this. So this slide is giving you the details about how we train the model. So first we do the pre-training on the ARDS cohort, and then we come to the COVID-19 cohort for the fine-tuning. So as I said, the COVID-19 cohort prediction task is to given a window for the patient. So we look at the patient as in a sliding window fashion, and then given a sliding window over time, so we look back last 2 days, or we can look back 4 or 8 days, and then we try to predict, will the patient be discharged in the next 3 days? We choose next 3 days because when you look at the distribution of patients who, how long they stayed, we can see that there's a sharp drop. If you look at the plot on the right, the x-axis shows the duration of patient stay, and the y-axis shows the number of patients who had the duration of stay. So really, right now, currently our outcome variable that I'm going to show you the numbers in the next slide is that we are always trying to predict, given a window in the past, will the patient be discharged in the next 3 days or not? So there are two type of numbers that's insightful to understand what's going on in the model. First one is looking at the number of performance from the pre-training step. That's what you see as predicting mask feature. So what this means is that if I go back to this particular slide and say, I'm going to mask out fever, I'm going to build a snapshot of the patient at a given point of time, I'm going to mask out fever, and I'm going to use the rest of the information in the green circle and see if I can predict the missing entity's fever. That's what I'm trying to do. And what we can see is that the aggregation of the patient stay, there is a trade-off that we can, if we aggregate the patient's information by 6-hour intervals, we get to 12% accuracy in filling in those missing entries. And once we take a pre-trained model and then bring that into the fine-tuning step, and we're trying to predict the length of stay, will the patient be discharged in the next 3 days? We can also see that there is a trade-off between the increasing, in this case, increasing the aggregation intervals leads to improvement in the performance. The final slide tells you about what happens if you don't use the pre-training cohort. What happens if you just train the model on the COVID-19 cohort? And you can see that the top half is just training a model on the COVID-19 cohort, and the F1 score is about 0.53. On the other hand, if we pre-train on the broader cohort, on the acute respiratory distress syndrome cohort, and then fine-tune the model further on this COVID-19 one, then the performance of the model significantly goes up to 0.677. But what is also perhaps very encouraging for this particular audience is that I'm showing very preliminary numbers, but once you integrate the risk factors, and this is one of the first things we have pulled in from the NLP data source, is that the performance of the model goes up from just using the drug codes and the diagnosis codes that we will be getting from the structured data, which is a very encouraging sign. So in closing, I want to leave you with 3 kind of insights. So what's a big idea is to build multimodal prediction models that are interpretable or explainable. And the way we think about this is that trying to use tools like Spark NLP to take diverse data sources, clinical notes, which are traditionally very hard to work with, and project them into the same symbolic representation where we can have quotes from the natural language nodes, codes from the drug codes or diagnosis codes, and even other type of information that will come from time series data sets. And then we can bring all the neural symbolic machinery. We can design algorithms that are interpretable, bakes in the clinical insights that tries to mimic how the doctors would think. The second point is that working with this kind of unified representation is very advantageous, because then you're not just throwing all these models, encoding them into vector space and feeding them into a deep learning in architecture, but you can also bring in all the traditional methods, item set mining and other symbolic methods, to really understand what's going on in the data. And I think that like, as you can see, that we could do a study by looking at the relationship between the top comorbidity patterns and the drug patterns, and kind of reason about what's getting better and what's not. And the final point is that being even though our results are very initial, but they look promising, that as you integrate the information from the natural language clinical notes with more structured diagnosis codes and drug codes, it is leading to better predictive performance. So that's all I have for you. And I'd love to take questions in the chat. Thank you.